Going to do is we're going to start the second section where we're not going to look at ordinary differential equations of where you got y as a function of x, but potentially you're looking at say z as a function of x and y, or w as a function of x, y, and z. And these are partial differential equations, and these are kind of in the real world is not one dimensional. It's three-dimensional and four-dimensional if you include time. And so you're led to these partial differential equations. Now, solving partial differential equations is very, very difficult indeed. And I think you're not gonna see any partial differential equations done until fourth year. But we're going to start by introducing them here and seeing how you can approximate solutions. So just in this week, we're just going to look at the idea of a partial differential equation and an example of one. Okay, so we're going to start with some theory from actually should have probably done in MATH7016. So in this technique, finite differences, you mesh the domain. So if you're looking at, say, for example, you're trying to analyze this kind of a shape, say maybe you're interested in the temperature distribution. Now, already you've got temperature as a function. There's two input variables, the x coordinate and the y coordinate. So this is a function of two variables. So what you can do is you can mesh it up. It's also referred to as finite element analysis. And this grid should be kind of a square grid. I mightn't be drawing it like that. And what you do is you replace the continuous, which derivatives where the h goes to 0. So that's like you're familiar with limit h going to 0, where you don't let the h go to 0 mathematically. You just let h be something small, and then you'll usually call it delta x. Okay, and what this does, it converts a differential equation into what's called a difference equation, and which also reduces to a diagonally dominant problem, a linear system, which I think I'm just going to write down probably here. So you're going to end up with something of the form ax, or let's say a v equal to b, a matrix equation, but a diagonally dominant one, which means that the solutions are kind of easy to approximate using Jacobi or Gauss-Seidel. The Jacobi and Gauss-Seidel methods, the way I do them, I think might be a bit easier than the way Bob might have done them. So this is all based on the definition of the derivative. So the derivative says that if the f dashed of x at a point, say x0, is what you do is you take 2 points that are close together, x0 plus h and x0, and you look at the rise over the run for them. Now, what we have here is that as h gets smaller and smaller and smaller, the thing on the right gets closer and closer and closer to the derivative. And what that implies is that if h, which I'm going to call delta x here, if delta x is small, and that should be kind of an if, then you can approximate the derivative at x0 using f x0 plus delta x minus f of x0 divided by delta x. And this approximation is gets more, the smaller that delta x is, the better this approximation is. So just think about what the thing on the left says. So look at this quotient, this fraction. As h gets smaller and smaller and smaller and smaller, it gets closer and closer to a specific number, the derivative, the slope of the tangent. So it's getting closer and closer all the time. So what if you start with h equal to 1, and just imagine h getting smaller and smaller and smaller and smaller. Suppose if you stop at 0.1, isn't that's going to, now you're heading towards the derivative. So if you stop at, say, delta x or h equal to 0.1, you have an approximation of the derivative. If you let the h or the delta x get even smaller, you're going to be even closer to the derivative. Okay, so let's see kind of an example of this. So consider a 10-meter rod cut into 5 pieces. Now here we're often going to talk about fairly large step sizes, but in practice you'll have much smaller step sizes. Probably not in the programs that we look at, but in theory you would know how to do it. So say this is x equal to 0 meters, I guess, x equal to 10 meters, and chop it up into 5 pieces. So this is a mesh. So the delta x in each case is equal to 2. Okay. So this is kind of what we've kind of written here. And now let's maybe, I think we're going to go with f is some value of the function. Now I could go with temperature, but let's say that it's a rod, and suppose that f is the temperature at a point. So let's take 3 points. Let's take, now they should be equally spread out, but they're not. And let's call this the point xi. This the point xi plus 1, considered the next point, and this to be xi minus 1, the previous point. So the x's there are just, well, I mean, they're 2, 4, and 6. Yeah? And what we're interested in is the value of some function at those 3 points, which you can think of as the temperature. So you've got the temperature at xi, in other words, at 4, temperature at the next point, and the temperature at the previous point. Okay. So you got points and value of function. You can think of the temperature there. So we can write down something here for xi. The derivative of the function at xi is equal to the limit as h, well, maybe we'll go to delta x now. Delta x goes to 0, f of xi plus delta x minus f of xi divided by delta x. So we're saying suppose x is equal to xi, we've already done that. Suppose delta x equal to h, or just delta x here now, is small, and xi plus h, so the difference between these, or maybe this is h, or rather xi plus delta x gives you the next point. Then you've got an approximation written down here. Now how does this work? So this is approximately, if we choose delta x in this case to be 2, f of xi plus delta x, so that will go from xi to xi plus 1. Maybe I'll slow that down. No, I don't have to slow it down, because so xi is actually equal to 4 and xi plus 1 is actually equal to 6. So if I do xi plus delta x, that's 4 plus 2 is 6. So that gets you to the next point minus the point I'm at divided by delta x. That's an approximation of the derivative. And so we get this formula here, that the derivative of xi is equal approximately the value of the function at the next point minus the value of the function where I am divided by the difference in x. And if you're kind of talking about it in terms of what's it like, it's the next value minus the current value divided by delta x. Now what about the second derivative? So this is going to be important. What about the second derivative? Well, the second derivative is the derivative of the first derivative. So you get this formula here. Now this is done a kind of a funny way, but it is actually the same thing, because maybe it's not always clear to you, but like say if you do a derivative at a point xi, the h can come from the positive side or the negative side. It doesn't really matter. So you can have h positive here, h negative here, and they both mean the same thing. The important thing is you have a difference of values of the function divided by the difference in the x, which I do have down here. So what are we going to get? So if we do the two formulas, you end up with this. Now where does this one come from? Well, we'll probably do that up here. So The first one is fine. What about the other one? So we're looking at the derivative at xi minus delta x, and that is equal to the derivative at the previous point, which we call f of xi minus 1. And we said that we can approximate the derivative at a point as the value of the function at the next point, which is xi, minus the value of the function at the present point, which in this case is I minus 1, divided by delta x. So that's where that is coming into. And you do a bit of algebra, you multiply above and below by delta x, and you see that there's two subtractions of f of xi, and there's plus f at the previous thing. And so that this is what, and you should have seen this in MATH7016. So this is the other finite difference approximation we have. How do you approximate the second derivative? You use this. So the second derivative at a point is approximately the next value minus twice the current value plus the previous value divided by delta x squared. Okay, so that's the stuff you need at the background. Okay, so that's kind of theoretical background that we need. Okay, now we're going to look at something called Laplace's equation, which is an example of a partial differential equation. Right. Now this can be a bit tricky, and it's one of the harder things I do in CIT is this lecture here, so hopefully it goes okay. So we're going to have a thin heated plate. Now it's going to be heated, so if you imagine just kind of, if I draw a picture of it here, so the heat transfer is happening at the edges. Kind of like, imagine like imagine a sandwich and the bread is insulated, and it's just kind of the you know where the ham is and the lettuce, that's where the heat transfer happens. So it's something like that. The top of the thing is insulated. Right, now it's thin, which means that the height is is essentially, you can imagine it to be 0. And what that means, if you do that, you're not going to have much temperature variability between, basically, essentially you're making the three-dimensional object, a plate, kind of two-dimensional, essentially, when you're doing that. So like if you zoom in, here's the side of the plate. This is the side of the plate. It's so narrow that there's basically not really space for much change in temperature. So how could I write this? Maybe I write that the change in temperature in the z direction is basically, forget about it. You can just imagine that it's constant, okay, which is a reasonable assumption. Right, so I'm going to place the plate here in a minute in an xy axis, and we're going to kind of just forget about the z. But it is there. It's really thin, and that's actually even exaggerated it. So essentially, you're imagining it. It's almost thin. It's thinner than that. Okay. So we might talk about the dimensions if we wanted. We could say that this maybe is let's just say L1 and L2. Okay. And what we're going to do is we're going to mesh it up into loads of little pieces. So imagine a square mesh. So I'm just going to do 2 bits. So I'm going to exaggerate the size of the mesh. So this is delta x, but imagine that it's actually not quite that wide. And have a delta y mesh the same. And delta x and delta y are the same, so it's a square mesh. So everything is a square. So imagine everything meshed up. Now this little bit that we're looking at, it does have a little bit of thickness, but even in relation to delta x and delta y, it's really small. But it's a little three-dimensional shape. The only thing is just I'm going to actually get rid of that bit, but just imagine it's essentially two-dimensional. Okay, so what we have, okay, we've got heat transfer at the edges. So there's heat. Now that could mean that there's heat going in or heat coming out. Depends, of course, heat flows from hot to cold. They look like loads of little integral signs. Okay, now if you leave this, eventually you're going to reach equilibrium. So what do we got? So steady state. So imagine this here. So like you can have different temperatures. So like at each point on the boundary, so we can actually talk about a boundary here. So if this is the plate we might call R, this kind of three-dimensional region around it is the boundary of R. And you specify the temperature, you'll know the temperatures at the boundary. So they could be constant or they could be given as a function. Now, if you just drop the plate, put the plate into a room, eventually you're going to get a temperature equilibrium. Now, what you can have in temperature equilibrium, you can still have a flow of heat. So if you imagine, I can never think of a good example for this. I really can't, but if you put a saucepan with loads of water, I think I'll be doing this soon, with loads of water on a hob, eventually, and say the hob isn't that hot, eventually you'll reach an equilibrium. Now, it won't be really steady state, because eventually, like the water, if it's say the water isn't boiling, so a roughly warm hob and a saucepan with a load of water in it. So what will happen eventually is you'll reach steady state. So if you look at any point on the pot, be it the handle, be it kind of the edges of the pot, the bottom of the pot, the air above the pot, or anything like that, if you observe it after a long enough time, the temperature will be constant. But what won't happen is the temperature won't be the same everywhere. So maybe the temperature out in the handle is colder than the temperature right underneath. But there is still a heat flow. So what steady state is, it isn't an absence of heat flow, it's an absence of change in temperature. So we'll just write down here, so steady state means that the change in temperature at any point, now here we'll talk about x, well I'll just write change in temperature is equal to 0. Or we could say that the partial derivative of temperature with respect to time is 0. That's what steady state is, but there is a flow of heat. But the way it must work for steady state, so just imagine this little volume element in the middle. The amount of heat going in must equal the amount of heat going out. If there's more heat going in than out, then the energy in that little volume element will increase and the temperature will increase. So whatever the heat flow is, whatever is going in must go out. So I'm not sure how exactly I'm going to draw that, but let's give it a go. So you're going to have, I'm just going to write heat energy at the moment. We'll probably do a bit better soon. And whatever goes into this thing, say for example through those walls, so that's what's going in. If it's to be in equilibrium, it must equal the heat energy out. Okay, so that's what we're saying at the time being. Okay, so the plate is insulated everywhere except at its edges where a boundary condition holds. So the boundary condition will be like, now we're going to assume that the plate is so thin that it's basically two-dimensional. So the boundary condition, where does that say? That'll be like, so it'll be a function from the boundary to the real numbers. So it's saying basically at every single point, it'll say, okay, here, what's the temperature there? What's the temperature here? What's the temperature here? That's what I mean by boundary condition. Usually it'll be like, oh, the temperature in the bottom is 100 and the top is whatever. Okay, but the boundary condition is actually a function. Okay, the insulation and thinness of the plate means that the heat transfer is limited to the x and y directions. So that's the other thing, it's so thin that you can't really, the heat doesn't really go up and down or anything like that. It just kind of flows in two dimensions. The plate reaches a steady state when the temperature does not change. That's the thing in red. If a volume element such as delta V receives a net heat energy transfer, then the temperature will rise. Therefore, for the plate to be in steady state, the heat energy transfer must equal the heat energy out. Okay. So heat energy is not uniform when in steady state. So this is something we spoke about. So imagine now maybe the water isn't boiling but warm, because if it's boiling you've kind of issues there, don't you? So there's the pot, there's the handle, here's the heat, say it's fire. And a bit of water. Water's warm. So the heat transfer isn't uniform. It goes in different directions. So you're going to have a big one here and a smaller bit of heat transfer there, something like that. This system can theoretically reach steady state with various components at various temperatures, but nothing cooling up or cooling down. So now we talk about heat flux density. We kind of have to explain this, and I think a lot of it is well explained by the units. Okay, so joules per meter squared per second. So the way you want to think about this is, so you have, say you got some flow of heat energy. It will have a direction. Maybe that's a bit difficult to imagine, but just say it does, right? So say this is the direction. Well, if you can, now the heat energy is not actually uniform. So if I move up a couple of centimeters, then it's no longer going to be the same value. So this is just Q here. But imagine that you did have a uniform field. So a really, really big field where there's just heat energy flowing. So what you can do is you could just capture a 1 meter square area, and you're going to have heat flowing through this. And how much flows through? This is 1 meter squared. How much flows through it in 1 second is the heat flux density. So if more flows through in 1 second, you've got a larger heat flux. And there is a thing here about it's a vector because it has a direction. So that's captured by the ijk. Okay. Now, so imagine our unit of area. Now our unit of area is our little thing here. So we'll do our best to draw this. Now we're going to make an assumption, which isn't a great one. So we're going to have a point here. And a point here. And we're going to give it coordinates. So this is going to have coordinates x, y. And this is going to be 1 over, so this is x plus delta x. That's in the wrong place. X plus delta, that's worse. Sorry, I'm sorry about this. X plus delta x, y plus delta y, because it's up in the y as well. So I'm going to assume that the heat flux density, which is different at all these different points, so all of the heat flux coming through this phase, we're going to assume is constant. So assume this is a constant field, assume, and what value are we going to pick? The value at x, y, the coordinate. Assume, so we'll say uniform field q of x I plus q of y j. Okay, so it's just a fixed vector, basically. So what does that vector mean? Well, it says how much it's flowing in the x, how much it's flowing in the y, and we're saying that it's basically the same. And then for the other face, as it were, for the out, so that's the in face, and this is the out face. So the out could be going in all different directions. But roughly, because the thing is assumed so small, we're going to assume that all those arrows are the same and that it's the same as this point here. So qx plus delta x I plus qy plus delta y j. Okay, now strictly speaking, it could be a little bit, that could be made, some of you are looking at that might be again, that's a bit weird. We're actually saying really that it's the heat flux density at x, y, and here we're saying really that it's the heat flux flux density at x plus delta x, y plus delta y. These things you see don't make as much sense. But anyway, okay. So now what I want you to do is think about the heat energy in and the heat energy out in 1 unit of time. Okay, the joules of energy enter either through the vertical face or the horizontal face. So the vertical face is this one and the horizontal one is this one. Now if you decompose all of this uniform field, now they're all basically the same, so we can just replace them with a single vector. It's composed of an x component. So like if I draw this vector here, right? I suppose I better just do this. So this is the vector coming in. So this is q arrow x, y. It's composed of an x part and a y part. This is the x part, which we're calling q of x I, and the y part we're calling q of y j. Now, in terms of where do the bits go, this bit goes through that face, and this bit goes through that face. So think about the heat flowing in the horizontal direction. It can't come under the bottom. It goes over into the vertical face, and the heat that's flowing up has to go through the horizontal face. Yeah. So let's now, am I drawing it again? I don't think I will draw it again. I think we're just going to write down how much goes in. We're just going to let's just write down something. So heat in time delta T. Okay, so the heat flux density is energy per area per time. So if we multiply it by area and time, it'll just be heat energy. So we've got the bit coming through the bottom, so that's equal to q y times the area of that. Now the area, we got a little delta z coming through, so that's delta x by delta z. Okay, and then how much time, delta t, plus how much heat is going into the vertical face. Q of x is going in the horizontal. What is the area of the vertical face? Well, it's delta y by delta z, and how much time is delta t. So that's the heat energy in. I think there's going to be space that we don't need. And then what about the heat energy out? Are we going to look at that? Let's just write it up here. There, we'll go back here. And then out, well, let's do the top first. So it'll be q y plus delta y times the area of that face, which is the same as the area down below, delta x, delta z, in the amount of time is delta t, plus what about the face on the right, which is the other vertical face. So the blue component, which I haven't drawn well here, this is the bit that goes, no, excuse me, the x plus delta x, that's the bit that's going in the horizontal direction, will go through the vertical face. So that's q x plus delta x, and the area is delta y, delta z, and the time is t. So this is how much heat energy goes in and out, and if it is to be in equilibrium, these must be equal. Okay, so hopefully this is going to give us something. So heat energy in equals heat energy out. So what have we got here? So now it says, oh, this can be rearranged. Well, let's do a little bit of the rearranging ourselves. So for start, and we'll do this for the next page, we can divide by basically delta x, delta y, delta z, delta t, divide both sides. I'm going to have to pause and write down what I have here though. If I divide both sides of this, as I said, what we will get, if you carefully do that, you'll have q of y divided by delta y, plus you'll have q of x divided by delta x, equal to q of x plus delta x over delta x, plus q of y plus delta y over delta y. And if you take the things on the left hand side away from both sides, then you basically get this formula here. Okay, so the problem with this is that it assumes that the heat flux density assumes only two values across. So this assumption about the fields being uniform is not a good one. Okay. However, the heat flux density should be continuous means that if you make the volume very, very, very small, there isn't much change between Q0 and Q1. Now, what's Q0 and what's Q1? Q0 is the heat flux density here, and Q1 is the heat flux density here. And I'm saying that if the delta V is very, very small, those things should be basically the same. And so the assumption that Q0 governs along the left and the bottom face and Q1 governs along the top and the right face isn't too bad. You can be a bit more careful and make this work really good. Now, how do you make this shape really, really small? You take delta x and delta y going to 0. Now, if you do this, you take limits. You take the limit as x goes to 0 and y goes to 0, both of them. Now, there's a bit probably going on here that, isn't actually perfect. There's something I can fix here. No, I'm not going to bother fixing it. I'm going to leave it deliberately woolly because it's a little bit tricky to do really, really well. But basically what you have here is the first thing, this is a derivative with respect to x, and the second is a derivative with respect to y. And now I'm going to do something that mathematicians do sometimes, which is hand wave. I'm not going to explain this fully, but you've got a derivative of q with respect to x and a derivative of q with respect to y. Now you can say, oh, like I could kind of cheat and say, well, q is a function of x and y, and so I need to use partial derivatives, but there's a little bit more going on there, which I probably need to be careful about, which I probably could be if I really tried. Yeah, I won't really try though. Okay, so this is the equation for steady state for the plate, that the partial derivative of the heat flux density in the x plus the partial derivative of the heat flux density in the y is equal to 0. So now what we use is we use something called Fourier's law of heat conduction. And it says that heat transfer is proportional to the temperature gradient. Okay, so what we're going to have is, how am I going to do this? So we've got a face. What the hell am I talking about here? Not sure. Okay. And then there's a face. No, I think it's just saying that there's it should be a face. This is an area, so it's a little square. Now the way it's done is it's a square face where it's delta y and delta x or something like that. That doesn't make perfect sense to me, but anyway, I'll just leave that there. So, suppose you got the temperature here is temperature of x, and the temperature here is the temperature of x plus delta x. So Fourier's law of heat conduction is a bit like Newton's second law. So Newton's second law says the temperature changes when there's a difference in temperature. So what Fourier's law says is that there's going to be a heat flow when there's a change in temperature. So where are we going with this? So I think one of these is going to have to be thinking here is that, yeah, so this is going to have to be delta Z and this is going to have to be delta Y. So this into the page is like the little thickness of the delta V. And so the heat flux, now the heat flux is, it's the heat flux density times the area. Okay, so the heat flux here is Q of X, say times I. The area is delta Y delta Z, and that should be proportional to the temperature difference, which is Tx minus T of X plus. Now, the reason that we put the T of X plus is because heat flows from hot to cold. So I'm saying that for the heat to go in this direction, I need that T of X is positive, bigger than T of X plus delta X. So that's why it goes like that. For it to be proportional means it's a constant times. And then what you can do here is you can, what's going on here? A bit of delta Z and nonsense going on is you end up with this thing. So this assumes constant heat flux to be more accurate. You make the 2 points to be closer together. And so you end up with Q of X is equal to minus K dashed over delta Z. And if you look at what's left there, it's the derivative of temperature with respect to time. Okay, similar analysis gives you the thing below. We're very, very close now. So if we put, so look at this, these Q's. So what does this say? Well, differentiate both sides of this with respect to, god damn it, and this should be an X. Differentiate both sides with respect to X. You get that the partial derivative of Q with respect to X is equal to, fix the constant minus K dashed over delta Z, and the derivative of the first derivative is the second derivative. And similar story, this is minus K dashed over delta Z times the second derivative of temperature with respect to Y. Now, if the thing is not isotropic, the K's are different and things are a bit messy, but we'll assume that it is isotropic. So what's our equation? That the sum of these derivatives is 0. So now put in these derivatives instead. So we get minus K dashed over delta Z, second partial derivative of temperature with respect to distance, minus K dashed over delta Z times second derivative of temperature with respect to the other distance is equal to 0. So if we divide both sides by K dash, multiply both sides by delta Z, we get Laplace's equation. That the second derivative of temperature with respect to one distance plus the second derivative of temperature with respect to the other distance is equal to 0. And this is your first partial differential equation. And this is going to be, next week we're going to study ways of approximating solutions to this. So you have the solution is temperature at a point xy. So your job is to solve. So it's not temperature as a function of a single variable. Temperature is a function of two variables. And solving that is not easy, particularly if the boundary condition is nasty. It's a partial differential equation. The first one you've seen, it's a relationship between a function and its partial derivatives. As I said, you'll see them exactly in fourth year, but next week we'll be approximating them. Okay, that's all for this week.